this is Mrs. Orton. I'm going to go in the notes for 7-1. It's going to be 7-2. So 7-1 is the exponential function of the graph. This should be a review of what you know too, so we will go through these fast but normal. What are we doing in this section? We're recognizing the graph of the exponential functions with the base of A. Graph exponential functions, recognize and evaluate exponential functions with the base B, which is the actual base, and then use exponential functions to model solve the right problems. So if I have an exponential function, that would be f of x is equal to e raised to x power. So in this case, it's b my base, and what I have to know about my base is my base is greater than 0, and my base is not equal to 1. And so my base is equal to 1, then 1 raised to any power is just going to say 1. So when I graph an exponential function, if I start with like parent, if I start with the parent function, let's say I say f of x, let's just say 2 to the x. So if I say that, then if I were to graph this and put this in my calculator, I would see that I'm going to go through 0.12, and then I'm also going to go through 0.28. And I got that by putting that in the calculator. I'm going to have a graph that goes something like this. So what I'm going to know about this is that my domain is going to be negative infinity to infinity. As I domain, remember, are my x values. And I can put any x value that I want into this exponent. My range is what my y values are going to be. Well, I can see here that I'm going to have this horizontal asymptote at y is equal to 0. It's not going to cross that line y is equal to 0. That's going to be my horizontal asymptote. So all my y values are going to be above that. So then my range is going to be from 0 to positive. And then if I want to do my x-intercepts and my y-intercepts, my x-intercept is when y is equal to 0. Well, that's my asymptote, which means there are no x-intercepts. If I do my y-intercept, that's when x is equal to 0. So if I put in 0 for x, so if I have f of 0 is equal to 2 raised to 0 power, well, that's just going to be 1. So then my x-intercept is going to be 0, 1. My asymptotes are talked about, it's going to be y is equal to 0. That asymptote is also going to be my range. And then if I ask for increasing and decreasing, as I look at this, it's a constantly increasing function. So it's increasing the entire time, so it's increasing from negative to positive. So that should be a review of what we did last time. So now let's talk about transformation. So if I have f of x is equal to a b, x plus or minus c, plus or minus t. So this, the b is still my base. That's still my base. So that's not going to change. Remember, my base is not equal to 1, and my base has to be greater than 0. But my a is the coefficient that's out in front. So the a is the coefficient that is out in front. What does that tell me? Well, if the absolute value of a is greater than 0, or greater than 1, I'm sorry, not 0, I'm going to have a vertical stretch. And these words should seem familiar to you. If the absolute value of a is less than 1, then I'm going to have a vertical compression. And then if a is negative, that means my graph is going to reflect over the x-axis. So here, now the c, this part here, this c, is plus or minus. If I have x minus c, and technically my c is positive, and this is going to be, I'm going to move c units to the right. If I had x plus c, then I'm going to move c units to the left. move my graph up or it's going to move my graph down. So that is going to be, if D is a positive D, it's going to be D moved up. If it's a negative D, then you're going to move D units down. So what does that mean? Let's look at a couple. So the first one, I have f of x is equal to 2 to negative x minus 1. So my parent function is going to be that f of x is equal to 2 raised to the x power. So the coefficient in front of this 2 is 1. So since it's 1, so since my a is technically 1, I'm not going to have, so I have no vertical changes. If I look at this, my b is 2, that's my base. My c, I'm not adding or subtracting anything, but I have this negative sign here in front, which means I'm going to reflect over the y-axis. The negative sign we're out here, I'm going to appear that the reflection of the x-axis. And then the last thing I have is this minus 1, which means that's going to be my d, which means I'm going to go down 1 unit. So let's do another one. Let me just add one, add an added, so you're going to have to add it to your note sheet. So let's say f of x is equal to 1 half times 3 times x raised to x minus 2. So if I do that, then the a is 1 half. So that 1 half is less than 1. So that's going to be a vertical compression of 1 half. And then the next thing that I have, my parent point, the parent function. The parent function is f of x is equal to 3 raised to x. And then have that x minus 2, which means I have x minus 2, which means I'm going to move 2 units to the right. And that's it. Let's do another one. So here I have f of x is equal to 4 minus 5 negative x. So the parent function is going to be f of x is equal to 5 raised to negative x. So the first thing I'm going to look at is let's go in order from left to right as I see it. So the first thing I see is this 4. That 4 is positive. That's my b. So I'm going to move 4 units up. The next thing I see is I see this minus sign. So my a is 1, but it's negative. So that means I'm going to reflect over the x-axis. And then I see in the exponent I have a negative x, and that negative x is going to be reflection over the y-axis. And just to be clear, that's the reflection of the y-axis, and then because of that one in front of the y, that's going to be reflected over the x-axis. I think we're good. I think we're good. So now we're going to move on. So the next one, we're going to talk about the natural base for little e, and you remember that there is a button on the calculator. That e is 2.718 all those decimals. So that just tells you that's like a natural growth. So when I have the limit as x approaches infinity, and I have 1 plus 1 over x raised to the x, that's what it needs to be. When the limit as x approaches 0 as 1 plus x raised to 1x, it's also going to be 3. If I were to graph that, I'm going to have a function that goes something like this. The function. So, well, e comes in very handy. We use it a lot, especially with interest times. So you learned to do interest times before. So if I have n where I'm not compounding continuously and compounds like n times per year, I'm going to take my rate, and remember my rate is going to be a decimal, and then I'm going to divide it by the number of times I'm compounding per year, and then multiply the number of times I'm compounding year by the number of years. That's when I tell you that I'm compounding annually, semi-annually, quarterly, monthly, weekly, whatever that happens to be. If I want to do more accurate estimate, like compound continuously, that's where the E comes in. So I'm not going to use the formula above, I'm going to use this formula that involves E. So let's do one. So I have a total of $12,000 invested at annual interest rate of 9%. Find the balance after 5 years for this compounded quarter. Well, quarterly means 4 times a year, so my N is equal to 4. So I'm going back up and I'm using this formula here. So I'm going to say the amount is equal to 12,000 times 1 plus, and then I'm going to take this interest rate of 9% and change that to the decimal, so plus 0.09, divided by the number of times I compound per year, which is 4, and then I'm going to raise it to that 4, because I'm compounding 4 times a year, times 5. So this will end up being 20, which makes sense, because if I'm compounding 4 times a year for 5 years, I'm compounding it 20 times. When I put that in my calculator, and do the work, I end up getting that my amount is $18,726.10. If I'm compounding daily, well, I'm going to use the fact that there are 365 days out of a year. So let's say my amount is equal to 12,000. 1 plus is still 9%. The now divided by 365, and we take 365 and multiply by 5. So I'm compounding it more, which means I'm compounding it with interest on interest, which means if I'm compounding more frequently, that means I'm going to have a higher amount because I'm making more interest. And when I do this one, I get $18,818.70. And the last one is continuously. And when I think of continuously, this is where I use parts, and I use small parts. And so the amount is going to be my principal, which is $12,000, times E raised to the 0.09% times 5 years. And when I do that on my calculator, I should have the highest amount yet, at $18,819.70. So that covers everything that you need to know from 7.1. And now let's talk about 7.2. Log functions in the graph. So the log function is the inverse of the exponential function. So we're changing the input and the output switch places when you do an inverse. So if I have a log function here, this b is going to be my base. And then when I graph a log function, so I put this in my calculator, and I'm just going to graph the same one that we did before, log raised 2 of x. That's going to be my x. And when I do that, I get a graph that has a vertical axis of x is equal to 0, and it's going to be a graph that goes so my domain, I have a restriction because there's a vertical axis. I'll never go to the left of that vertical axis. So my domain is 0 and then positive infinity. Remember, my domain is my x values. My range is my y values. And my range is going to be negative infinity to infinity. Remember, it's going to be the exact opposite. Those two are going to switch places from what my domain and range were from the exponential functions, because that's what an inverse does. The x and the y switch places. My intercepts, if I find my x-intercept, that's going to be y is equal to 0, and that ends up being 1, 0. And then my y-intercept is going to be when x is equal to 0. Well, I have a vertical asymptote for that, so I'm not going to have a y-intercept. When I look at this, my function is still increasing. But now it's increasing on the interval from 0 to 1,000 infinity. So, before we had the base raised to the exponent was equal to the value. Now remember they're going to switch places. So now I'm going to have the log base value exponent. So this one says rewrite in inverse notation. So in other words, rewrite as an exponential function. So this is my base 5. This 2 is my exponent, and it's equal to 25. If I do the next one, I can think of this 64. Now this is an exponential function because I have 64 raised to the 1/3 power is equal to 4. I just rewrote that in the root. So now what I can do is I can say my base is 64. So log base 64 from this here, 4 is equal to 1/3. So remember again, when you do an inverse function, these two switch places. So to evaluate the log by hand, so this is where I take the calculator away. I like to set it equal to something, so I say let's say equal to x. So I'm going to say 36 raised to what power is equal to 6. Well, I can make life hard. Or I could say, well, realize if I take the square root of 36, that's going to equal 6. So x has to equal 1/2. This one, 32 raised to what power is equal to 1? Well, anything raised to the 0 power is equal to 1, so x is going to equal to 0. This one is 2 raised to what power is equal to 8 raised to 1/2 power. Well, in order to do this, these have to be the same base. So I'm going to leave this 2 raised to x. 8, remember, I can raise this. 8 is 2. It's a power of 2, so it's 2 to the 3rd. That's my 8. And this is being raised to 1/2 power. Remember, when I raise a power to the power, I multiply. So this will be 2 to the x is equal to 2 to 3 halves. Once these bases are the same, then I can just simply say that the exponents equal to each other and say x is equal to 3 halves. You should remember that from algebra. Okay, if I have a natural log, the natural log has a base. The natural log has a base of e. So that's going to be ln x. And so it's understood to be a base of e if I see the ln. If I have a common log, that's understood to have a base of 10. If I just have log without a base written, something like that, then it's understood to be 10. Properties of logs, if I have n, so this has x equal to 0, it's like a raised to what power is equal to 1. Well, any number, in order to get 1 for an answer, that means I take any base and I raise it to 0. So in this case, this will be 0. And this one is saying a raised to what power is equal to a. Well, since these two are the same, so if the base and the number here are the same, then the log has to be 1. The exponent has to be 1. Then this one, I'm going to say, I like to write it in this exponent. So I say a to the x is equal to a to the x. Well, this is x and this x. The next one, if I had a natural log, so remember that means base of e. So e raised to what power is equal to 1? Well, that's going to be the same as this. That's going to be 0. This one's saying e raised to what power is equal to e? That's going to be 1. Then e raised to what power is equal to e to the x? And that's going to be x. So this variable is this one will stay the same. So now I'm sure we're going to get to do some by hands. This one is saying evaluate the log by hand. So this understood is to have a base and an exit. This is understood to have a base of e. So I can rewrite this as log base e of e to the negative 4 and do that if I want to. Probably wouldn't do it, but that's what it means. So we say e to the x is equal to e to the negative 4. So this whole answer is going to be negative 4. This one, remember, with nothing written here, it's understood to be 10. So this is saying 10 to what power is equal to 1 over 1,000. And when this 10 to the x, this the exponent is equal to that, so the log base value is equal to exponent. So it says students in a mathematics class are given an exam and then retested monthly with an equivalent exam. The average scores for the class are given by the human memory model of f of t is equal to 80 minus 17 times log t plus 1. T is the time in months, and t has to be between 0 and 12. What was the average score on the original exam? Well, their original exam, and t would equal to 3, because it's no months in between. So I'm going to say f of 0 is equal to 80 minus 17 times the log of 0 plus 1. So this is going to be 80 minus 17, and then this is 10. This is a base of 10, and I'm going to evaluate that. And I'm going to, and that'll end up being 0. So thinking of this, this would be 10 raised to what power is 1, so that's going to equal 0. This would be 17 times 0, so I'm going to do this. So the original is going to be 8, there is no average. Then what was the average score after 10 months? I'm just going to say t is equal to 10. So I'm going to do f of 10 is equal to 80 minus 17 log 10 plus 1. So there is no, the only way you can really do this one, because you can ask yourself 10 raised to what power is equal to 11. You're not going to be able to figure that out. So you're going to throw that in your calculator, and when you add the 80, you're going to end up with 62.3. So the average after 10 months is going to be 62. And I believe that's it. Yes, it is. So I will see you next